Okay, it's time to start the first natural science seminar of the spring semester. Those of you who are doing natural science seminar reports for my class need to make sure that they come from this semester as opposed to all of the other things that are loaded up onto the YouTube site, right? There's old stuff, but if you're going to write about something this semester, it should be from a speech or a presentation for this semester. So today, the Natural Science Seminar features David Sellers. Naturally, as soon as I want to talk about something, blanks out. Okay, so this is his bio from, not from here, no, because David Sellers is famous all over Michigan. See, he's really famous because he got a ton of money back in 2012 for being super smart. Brainiac Sellers, that's what we call him. So, I'm very happy for David, and you can go to this website, Western Michigan University's website. I think it's, I'd have to give you the connection. But anyway, he's good. This is his professor, his supervising professor, Dr. Schofers, over at WMU, and that's Dave, you can tell. So, some good things about Dave. He did work here, and he did his senior thesis under my tutelage, so I like to think that he knows everything about column chromatography. If you've had one of my classes, you know what I'm talking about because of my influence. And maybe he's going to learn a few things over at Western. You did? All right. So it's helping him out. See, it's not totally worthless, all the training that he does here. He was also a laboratory instructor for me, so he was the one who taught a few of the lab sections that I had, and that made my life easier. So maybe after he gets done at Western Michigan, we can do some other things, which would be wonderful. So what I'd like to do now is just move into having Dave make his presentation. He is representing Western Michigan University's chemistry department, so those of you who have interests in graduate school, especially in chemistry, put your ears on and listen. And he's also going to talk about his actual work. So David, if you would come talk to us.
Thank you for that kind introduction. Good morning. For those of you that were in my class a couple years ago, it's been a long time and I'm really bad with names. So please remind me, if you come up and talk to me, please remind me of your name. I also have propaganda.
Yay!
So if you're interested in Western at all after the talk, come talk to me. I have flyers with forums, and I have really cool stickies with a border and pestle. So I don't have much, but I have some, so first come, first serve on the propaganda. Before I started my talk, I want to point something out. So for those of you that have done Gen Chem and Organic, and preferably analytical chemistry as well, there's a really great undergraduate program that's run in the summers. It's called Research Experience for Undergraduates. Nationwide program. There's about 200 or so university sites across the country that host the summer program, and they gear the program towards picking up students that are minorities and those from small colleges that don't get a Tier 1 research school experience. So I highly recommend it. In particular, people from Spring Arbor are rather well liked at Western right now, so if you do want to apply, let me know. My lab will have an opening, and there's another neighboring lab that will have an opening too, and I can put in a good word. Just let me know. But this experience is great. It looks really good on a resume. It is a nationally known program in the sciences, so it's a good thing. So remember, if you've done organic and hopefully analytical too, this will be a good shot for you. Okay. So I'm going to give what is a rather strange scientific talk today. So most scientists, they go out, they try to sell their ideas and sell their research to the public. Because in science, you're not known unless other people start picking up on your ideas, they like them, and they carry them on. Instead, you're all here today essentially for the funeral of my research project. So what I'm hoping you will eventually get out of this is that you can see that when you go to graduate school, not everything will necessarily work the way you want it to right off the bat. And hopefully it'll give you some hope as to what happens after you do have a project that dies. And a little bit of kind of insight as to how projects do start, how they die, and how you live through it if you're a grad student. So when Dr. Baldwin invited me, he didn't know we were actually in the process of scrapping this project. Sorry, this.
Yeah, I don't know why it's not sized properly. Save us.
So yes, funeral, hence the black tie. I kind of gave away the punchline early, but I'll take you through what my lab did. So about 10 years ago, the Department of Defense and NATO as well realized that there weren't very many good methods for detecting nerve gases if a terrorist attack were launched anywhere. Typical methods, they were either slow, they relied on enzyme-based tests that had a color change. Those were typically slow and unwieldy to perform, and also don't really work well for testing stuff with the gas phase. And then other things they weren't portable. So mass spectrometry is this really great way of detecting things, but at least 10 years ago, they were big, you couldn't really take them into the field, and you couldn't find out what was there. So the Department of Defense poured, I would say, $20–30 million worth of money into academic labs around the country and gave them the mission, please find us a better way of detecting nerve gases. And my advisor was one of those people that got the grants. In particular, the Department of Defense, they said, please find us fluorescent molecules that can detect these agents, because fluorescence is really popular because equipment for detecting it, if you've taken courses with Dr. Kunzelman and you've seen ocean optics materials, they're very portable. The science behind fluorescence and absorbance is well known, and so they're very popular still. Though, to say this, the mass spec people are convinced that within like 50 years they're going to have a portable handheld mass spec to go out in the field. So fluorescence is probably going to die at some point, but it's good. So nerve gases, they work by inhibiting an enzyme known as acetylcholinesterase. Now this is important when a motor nerve sends a signal to a muscle. It releases a neurotransmitter called acetylcholine. Now for your muscle to be able to relax after this, that acetylcholine has to be broken down at the end of the muscle. So acetylcholinesterase is what does that. Now when a nerve agent gets in your body, it goes to that enzyme and it ends up binding irreversibly to that enzyme. Now when I say irreversibly, that's not quite true, but that's what we'll say for now. And so this prevents any acetylcholine from coming into the enzyme, can't be broken down. At that point, your muscles can't relax. So if you think it's your diaphragm, this doesn't really work so much on smooth muscle, but if it is your diaphragm and it can't relax, you stop taking breaths. So most people die by asphyxiation due to respiratory distress. So as you can see here, this is a list of the most commonly identified nerve agents from NATO. I believe it's sarin is the one that might be known most. In 1995, there was a terrorist attack on the Tokyo subway in which a few people died, so that is known. Now you can see from common themes, they all have a phosphorus atom connected to a double-bonded oxygen. Many of them have a leaving group, for those of you that have taken organic, and a leaving group that is at least a moderate leaving group. So fluorine, you might not think of it as a good leaving group, but it's okay enough that it works in this chemistry. Or a sulfur leaving group, or chlorine for some. So in my lab, there were several students working on projects on this in parallel. So when we're finding out it doesn't work, we're kind of all finding out that our individual experiments weren't going to work at the same time. So our first hypothesis we went with, and this was tested by the doctoral student that preceded me in the lab, his name is Lars Kohler. He thought that if we take a molecule, I will explain more about the structures in this later, but this is a 1/10th unit, and this is an aminopyridine unit here, that if we react it with our nerve agent, our organic phosphorus compound, that since phosphorus likes oxygen bonds a lot, it's a very strong bond, it should be able to react easily with the alcohol group here. And that's known chemistry, that's very common, that should work pretty easy. Now, once we do that, this alcohol group, if you remember activating groups in, I believe, SN2 reactions, if you convert an alcohol to something that will be a more stable leaving group, it should be able to leave much easier. The reaction will work better, and it will go faster. So the hypothesis was that this pyridine unit there's a lone pair on this nitrogen that could let it act as a nucleophile to displace this organic phosphate. It will then cyclize. I'm going to step back a little bit. We're going to talk about something real quick. So in fluorescence, I don't know if you've ever seen a diagram like this before. It's called a Jablonski diagram. Now these lines here, they represent energy levels. So if you think this is your HOMO, your highest occupied molecular orbital down here, and this is your LUMO, and each of these little lines, you might not have seen this yet, but these represent vibrational states that happen within these electronic states. So you can almost think that maybe these vibronic states are superimposed on the electronic states. So when you shine a beam of light on this compound, our hypothetical fluorescent compound, you can excite it, and you always excite it to a higher vibrational level, and there's some rules behind that that are really complex and not for us to talk about today. From there, the energy from that, when it's being dissipated, it will leave it in the form of, rather than it's currently stored as electronic energy, it's going to go away as kinetic energy, released as heat, down to your base level of your LUMO. From there, this can then emit light. That's what fluorescence is. This is your fluorescence. The one thing to notice, key thing to notice is, first, the energy, or the magnitude of your energy for your excitation is bigger than your emission. So if you excite something to high energy like a UV, your emission is going to be more down in the visible light portion of the spectrum. Another thing to note is, not only do you dissipate energy as kinetic energy within your vibronic levels, you can also dissipate it by dropping from here to there by a kinetic action. So there are ways that this molecule can relax down to the ground state without emitting light. Now, one of the things that will cause that is if you have a molecule that can easily rotate its bonds. So think of it as being kind of a loosey-goosey molecule. It can wiggle around quite a lot. So this molecule here, you can see, has a lot of free bonds here. They're not tied up. So this ring can rotate. The bonds in the alcohol and the amine, they can vibrate around and also rotate around. But when we tie it up like this, it can't rotate anymore. Now the hope was that this molecule here wouldn't be able to fluoresce because all of its excitation energy would go away as heat. But this molecule hopefully would, because it can't dissipate it that way. It can't wiggle its energy away. So this would be an example of something we call a turn-on sensor. In this case, it's not fluorescent. When it finds the sensor, it becomes fluorescent. So you turn on the fluorescence of the molecule. And these are the most prized of sensors. If you can attain this, you have a really good molecule. One other thing I need to tell you about is when you do absorption graphs and you have a reaction where A leads to B, A can absorb light, B can absorb light, you're going to see something that looks like this. So you have a lot of A, you'll have a really high peak, and for B you'll have nothing. As you make less, or as A becomes B, you'll get less A, more B, and so on, until you have all B, no A. Now you can see here, all these lines are meeting at one point. There's a particular word for this, it's called the isobestic point. What this means is that is the spot in here where A and B have the same absorbance value. So no matter your molar ratio, no matter how much A and how much B you have, it's always going to absorb the exact same at that spot. Now what might cause it to not absorb at that spot? If possibly A also makes C, or if B breaks down into D. So if you have a second or third reaction happening, you won't get that isobestic point. And you're going to see that will end up being the fatal flaw for all of our compounds. So you can see here, this is a titration graph. So we took that sensor I just showed you on this page, we took this molecule, we titrated it with DCP, which is an organophosphate like this. So we're hopefully going to see this reaction. You can see now this peak here is with no organophosphate in the compound. We have a nice absorbance here, and you can see there is not much of an absorbance there. So we can see as we put more and more in, this peak drops and this peak goes up. So something is happening. It's good. That's a good sign. Something is happening. But here are the problems. First, remember how earlier I said you excite with higher energy, you emit with lower energy. So the high energy portion of the spectrum is here, lower energy is here. So our emission, as we continue to get more of our B product in reaction, our emission wavelength is actually going to a higher energy state. This is a problem. Because remember, our emission is now at a higher energy state, our excitation is also at a higher energy state. So our emission is actually going towards our excitation wavelength. And this causes a problem in the instrument, because then you get some carryover from your excitation light that you're beaming into your sample, and you're going to end up seeing that in your a little bit in your emitted light. So that's the first problem for this compound. Also, look, you notice how on the board here, all of our lines meet at one point. There isn't actually just one point in this graph, is there? It looks close. It's close, but it's not. Especially you can see this line here. It's actually straight away from this point here by about 20 nanometers wavelength. So that is a small enough difference that the sensor just has a problem. It doesn't work, because that means there is a second or third or fourth reaction going on in the flask. So it's a problem. It could be remedied though. We're talking about nerve gases, right? That's what we're trying to detect. Nerve gases are in the gas phase. This is actually being done in solution. This is being done in chloroform. So chemistry where a gas will meet a solid is very different from chemistry where it's all dissolved in the same liquid. So there's a possibility, if we ran these reactions with a nerve gas in the gas phase, that we would have a possibility of not having a second or third reaction going on. So we might get a true isobestic point. Does anybody know what the problem is with trying to conduct a reaction with nerve gas? Exactly. There are some places around the country and around the world that do have the equipment to do it, but even if I had it, I wouldn't do it. I have a child and a wife, and neither of them would be very happy if I killed myself or a sensor. So wise. So this sensor, we won't say it's dead in the water, but it was put on the back burner for the reasons I just mentioned. So we came up with a second hypothesis in the lab. We said, okay, we saw with our molecule we wanted to make a turn-on fluorescence molecule. We were hoping to see that it wouldn't be fluorescent, and then it would. It turned out it fluoresced anyway. So we thought, as long as we're using our 110-phenanthroline base, and we'll talk a little bit later about why we use that base so often. As long as we're using that, we probably can't avoid fluorescence. We probably can't develop a turn-on sensor. So there's another type of sensor, it's the opposite, it's a turn-off sensor. And that's where you take a molecule that is fluorescent, so it's going to start off fluorescent, and then you're going to do something to make it stop fluorescing. Remember how I said earlier, if your molecule can wiggle about, if it has a lot of things that can rotate, it's going to be able to come back down to the ground state without emitting light. So that was our goal with this molecule. You can see this group and these bonds here are all, there's single bonds involved, so they can all rotate. In particular, the alcohol group is very good at wiggling away energy. So we said, all right, maybe this will be somewhat fluorescent, but not terribly. In particular, this is called a naphthalene group. So this naphthyl group is fluorescent on its own. So we said, all right, it's going to start off fluorescent. Maybe we can quench that, make it even more wiggly. So our hope was, we've also seen chemistry where the nitrogen group with its lone pair, if you remember, nitrogen is usually a pretty good nucleophile because it's also a good base. That would be able to attack the phosphorus. The leaving group would then leave. We'd have this phosphate group now attached to the nitrogen. Since we were talking about the naphthyl group already has pretty good fluorescence on its own, maybe if we stick the phosphate group up here, maybe it'll be able to wiggle away its energy. Already, with our hypothesis, there's a problem going in. We didn't really think about it at the start, but remember back in our reaction before, where did that phosphate group react? React with the oxygen. Where do we want it to react now? We want it to react with the nitrogen. So we're already trying to change the regioselectivity of the reaction. We did have some reasoning behind what we did. We were hoping and kind of assuming that this group is pretty bulky. It's pretty large. We were hoping that would protect this area. It would be so big, it would prevent that phosphate group from coming in here. It would want to react up there. I'm not even going to show the graph. Our second hypothesis ended up, it was a pretty big failure. We ended up with several different peaks in the absorption and emission that suggested we had several different reactions going on. So it was a problem. So continuing to eulogize, I'm not really speaking fondly about these reactions, but we're giving it a funeral. So the third hypothesis, and this is finally starting my research. So those previous reactions were all performed by different people, running in parallel with mine. So I'm now working on our third hypothesis, or I guess I'm trying to give them chronological order even though they didn't have one. So it's just, it's what I did. So in the lab, I mentioned a man named Lars Kohler earlier. He was the grad student that preceded me. He was trying to make compounds that looked something like this for a while. Your ketone and your amine, so this is a ketoamine. This pocket here, a ketoamine, is a really good binding group for a lot of things. It binds metals, it binds a lot of basic anions through a lot of different ways it coordinates stuff. So these are really popular to use in sensors. Well, one day while Lars was trying to make this, he was starting with some of the functionality you saw earlier. Starting with this. This is, well, we'll come to it again, but this is an amino alcohol, named for the amine and the alcohol. He's trying to convert that into that, and you're using, this would be an oxidation reaction. You want to take away some hydrogens and some electrons from this. So he's using what's a rather gentle oxidizing agent. So if you use a really strong oxidizing agent like potassium permanganate, if you remember from organic, that tends to blow molecules apart. Just kind of chews up those carbons and turns it all into carbon dioxide. So he's using a much gentler one, manganese dioxide, to make that. Well, lo and behold, if this R group had a methylene, a CH2, attached to that nitrogen, it actually ended up forming something like this. So it cyclized and oxidized quite a lot. Ended up, I think it's about 6 electrons that are taken away from the system to make that. And we'll get into this a little bit more in a bit. So in seeing this, when I got to Western, my advisor said, hey, this is some interesting chemistry, nobody's really done it before, why don't you try it and see if you can apply it to these nerve agents too. So that was my task when I got there, was to explore the reactions to make this, see how versatile they were, how clean they were, etc. And then try and do some chemistry with that. So my hope was, we've seen evidence, and we've also have some anecdotal evidence from other labs, that this lone pair on this nitrogen will react with that phosphorus group pretty easy. So hopefully we could end up making a molecule. This would end up, as we saw earlier, hopefully it would wiggle a lot and quench our fluorescence. Hopefully. You'll see what happens in a little bit. So what exactly is that first? That is, so we use the term heterocycle. Heterocycle refers to a ring structure that has carbons plus another atom in it. So it could be oxygen, nitrogen, sulfur. If it's another atom in the ring, it's a heterocycle. So this is named the oxazole, refers to this group in red. So ox for oxygen. The AZ prefix, aza, is an archaic way of naming nitrogen compounds. So the AZ refers to this nitrogen in the ring, and the OLE ending is a really common ending for heterocycles. Down here at the bottom, we have our 1,10-phenanthroline unit. So what's so special about this? Well, one of the reasons why we use this so often, my advisor is the world expert in 1,10-phenanthroline. You'll find if you go to graduate school, whoever you work with, they're the world expert in something. It's not very hard to become a world expert. You'd be surprised. You only need to take about 100 hours, learn about something obscure, and then you're pretty much the world expert on it. So we stick with this. And it gives us a lot of diversity that's available to us. The way these two nitrogens are positioned, nitrogens, remember, they have a lone pair. So if they're a little bit negative, they have a negative charge on them. So if something with, say, a positive charge were to come in, it would be very attracted. This is actually very good at binding metal cations. So in a whole wide range of them. The first row transition elements, it binds almost everything from there through there. It binds almost all of these metals. It will bind these in some oxidation states. And we even have evidence that it's binding magnesium and calcium and strontium. So that for being able to interact with various metals, this compound is almost the king of it. And we use that. Metals offer you a whole range of possibilities. They change the electronic properties around, so you get different absorbance and fluorescent values. They sometimes will stabilize the compound. sometimes they give you a good way of marrying it to a solid phase. Remember how if we want to detect a nerve gas, we need to have something to detect it. So if you want to put your compound in a solid that will then detect your nerve gas, you need some way of getting it onto the solid stably. That'll do that. So our way of approaching these, you'll see the rest of the scheme in a little bit, but we start with a material where we take, this is the 1,10-phenanthrylene itself, and we make this unit here, it's called an epoxide, or an oxirane, depending on how you learned it. From organic synthesis, you remember epoxides are really versatile because it lets you couple one carbon bond to another carbon bond if you want to, or you can react it with a whole host of other nucleophiles. This is actually surprisingly easy for us to synthesize. So if you think about aromaticity, this molecule does have Huckel number. It's almost a ring. It's somewhat aromatic. But you see here, these two rings here, they have the 6-membered ring. These have a high level of aromaticity to them. This bond here actually almost acts as an isolated alkene. It's almost not aromatic. So it actually goes...
my lectures.
So it reacts almost as you would an alkene. So we react this with sodium hypochlorite bleach. This household bleach. We go out, I go to Meyer. I used to buy Jump brand from Meyer until, I can't find a single Meyer brand bleach that doesn't have a scent in it now. All scented, it's all cotton or rain or all scents. So this is now Clorox bleach. Pour it into the flask, let it stir, and it's done. We recrystallize it to take care of it, but it's pretty simple. So we take that and then we do a ring opening of an epoxide from organic chemistry. So we have a nucleophile here. We use our nitrogen. That will react with, remember this carbon will have a partial positive on it because the oxygen may bring it. So nitrogen acts as a nucleophile, reacts there. This bond will cleave, giving us, eventually once we quench it, an alcohol and an amine. And we use some kind of Lewis acid to promote this. Remember, Lewis acids, they're electron pair acceptors. So what that will do for us, that Lewis acid will bind to our lone pair on oxygen. It will then slightly weaken these bonds between oxygen and the carbon. That makes it so our nitrogen is more active. And you'll see we have a couple options for Lewis acids that we go with later. And then once we have our amino alcohol, then we, as I mentioned earlier, we oxidize that. Just use a gentle oxidizing agent, and it quickly cyclizes and oxidizes. So one thing that should be noted about the chemistry here, there's several ways to make that reagent. It's difficult to buy. You typically have to make it in the lab. And you can actually make this there's an acidic way to make it, there's a neutral media way to make it, and there's a basic media way to make it. So for the basic reaction, you stir potassium permanganate, manganese oxide, and sodium hydroxide in a beaker. You give it 2 hours or so, and it's done. But you tend to have a lot of unreacted sodium hydroxide left over at the end of the reaction. And what that ends up doing is that will bind, it will kind of adhere onto the surface of that manganese dioxide. So when we wash this in our lab, we only wash it down to a pH, so the filtrate that comes through it is a pH of 10. So it's still basic, there's still some hydroxide anions floating around. So from organic, if you remember your E2 mechanism, you have a strong base typically involved that comes in, deprotonates things, and that's how you get stuff. That's how you end up getting things to leave. So even though we don't actually have an E2 mechanism here going on, we do think that our base may be helping to get this to at least cyclize in the first place for us. This acidic way of preparing this media is really complicated, so we haven't done it to actually find out if that's true, because it works. We don't really need to fiddle around with it at this point because it does work. So at this point, our lab is prepared. Not shown here are an additional eight compounds that were made before I got there. So I prepared 16 since I've gotten there. Using, you see, the amine here that I would have opened it with, plus a methylene in this compound. There's a bit of a reason for the variance in yields. So some yields are really high, because in these two, I can just evaporate all my excess amine, any side products, I can evaporate those away. They just leave. And I actually get a pretty clean compound in it, and I don't have to do anything to clean it once I'm done. But for some of these, this one I had to do a washing on. There's enough polar atoms in this, actually, some of the compound leaves with the water when I wash it. for this compound really hates almost every solvent that you can use. And so for that reason, it actually ends up just adhering to the alumina that I have in my reaction. Won't come off. So, but for the most part, it is moderate to high yield, fairly clean. Unfortunately, most of these have to be cleaned up with a column. Column chromatography is key to this, getting this chemistry to work. Unfortunately, they're a pain. They take a couple hours of your day as you slave away. Yes. Actually, a few of these are hot off the press. These 3 reactions were done this week. So you'll see in a couple slides I don't actually have data for the next step. So here's a representative NMR of these. So NMR is used to help identify how is this molecule actually shaped. So NMR, it uses a radio wave that interacts with your hydrogens in your compound, or specifically one isotope of your hydrogen, and for this, it's called the proton, so it's H1. We use that there. So based on where the hydrogens are on the spectrum, so there's a hydrogen here, they're all over the place. Based on what atoms they're next to and where they are in the structure of the hydrogen signal. So for these 3 protons here, we end up having their signals all in the aromatic region, so between 7 and 9. Some of them are a bit deshielded because of the nitrogen atom near them. The real key to identifying these structures, though, is this peak here and this peak there. Those are, it's hard to see on this structure, but those are doublets. They're split once, so that means they have one hydrogen that would be a neighbor to them if you had your NMR lectures. So those represent the hydrogen that's off of that carbon and the hydrogen that's off of that carbon. So they each have one neighbor, because we don't count our polar protons there. And so they show up very nicely. And this is actually, this stays true based on that positioning across all the compounds. So when I make these, you always look right there. It is an assumption, so sometimes you can be fooled. I was once, but it is. Then we have our methylene that is next to the nitrogen. That shows up here. And then finally our methyl group. So this is a very simple one. The larger structures that have more complex groups do have more peaks to them. And our second step of this chemistry, this is the oxidation step, as we saw from earlier. These yields, actually the crude yield of these reactions is actually about 100%. Typically these reactions go to completion, full product every time, with just a slight bit of impurities, a couple percent typically. Problem is, one of the best ways to get these compounds isolated is by recrystallization. So unfortunately, even with a pretty good yield, you end up losing some of it to the supernating of the recrystallization. So you end up with pretty good yields for some of these, others a bit poorer, depending. Now some of these you see there's no reaction yet. For these, the reaction hasn't been done. For this compound, the reaction, for whatever reason, didn't go. I'm guessing the reaction didn't go because, once again, as I said earlier, this group doesn't want to dissolve in hardly any solvent known to man. So for that reason, I think I had a hard time interacting with the manganese dioxide. It wouldn't react. And finally, when we have just a methyl group here, I have a hunch that this methyl group is not able to actually get close enough with that oxygen. It's not able to have the proper the geometry involved to get that cyclization to happen easily. And so this one hasn't reacted. I have high hopes for it, though. I think if I put enough heat into the reaction, things will fly around enough, and hopefully it will work. So that's making this. So it's pretty straightforward as far as chemistry goes. It's not. I mean, it's kind of just dump and stir chemistry. There's not too lot of difficulty. There's not a whole lot of finesse needed for these. And there, sorry to say this graph got shifted, but we can still see a little bit. Our aromatic peaks will still be around, so they'll be over here. You can see now that there's no hydrogen present here or there because of the bonds, nor is there any hydrogens on this carbon. So all of those hydrogens that we originally saw in the previous structure are no longer there. So all we'll actually see from this is the 3 hydrogens off of this methyl group, which appear at 3. I think that's a methyl group, maybe that should be around 1, but do know that it's really deshielded. This ring has aromaticity to it. And so for that reason, that will be acting more like a methyl off of toluene. Okay. So here is the death knell to my research. This next compound is what pretty much caused us to scrap the whole project. So you will see Okay, so this is a compound. This was a compound, of all my compounds I've prepared, this was the one that could most easily fluoresce. So this is a compound, it starts off, we have high hopes it will have good fluorescence, and then hopefully it will be quenched later on. So I make my amino alcohol. You can see once again we have our aromatic peaks, plus these aromatic peaks that all show up between 7 and 9. We have our peaks at 4 and 5 for these two hydrogens. And we have our peak for the benzylic hydrogens right there. When we make the oxazole, once again we lose all those hydrogens we lost earlier. So we actually have no sp3 hybridized hydrogens left. sp3 hybridized carbon hydrogens left. So we have all aromatic hydrogens. So what on earth is this peak down here? What is that peak? Water. This compound, for whatever reason, it could be something with the electron withdrawing of this side of the molecule, binds water in this pocket really, really well. We have a lot of evidence that our structures that have electron withdrawing units, this side of the molecule bind water tightly there. Most common drying agents won't dry it out. Nothing will get rid of it. The only thing that might is phosphorus pentoxide, but even that's iffy. So it binds water very strong. So it's hard to get rid of, and that actually could be one of the problems coming up. So we took this molecule, along with others that were made, but this one in particular I'm going to show, put it to just a normal absorbance spectrum. We see we have an absorbance in the UV. That's very common for organic molecules that have aromatic structures. So we have that. Next we need to see, does it actually fluoresce? So we know it absorbs light, does it emit light as well? So you can see here, 0 is actually, it's buried, it's somewhere deep within here. We do actually have a fluorescence peak. Now this is a hard graph to interpret, so I will try to walk you through. So 0 through 40, they all have this shape to them. That's it. That one spike is 0 through 40. Then suddenly, when we go to 50, we get the shoulder. So the spike lowers a bit, and we get the shoulder. So what's going on there? There's a couple things. So first off, we don't have an isobestic point. So we already know A going to B is not what's happening here. So we don't have a viable sensor at this point. And last, perhaps, what's going on here is we're actually seeing a peak just start because kinetically the reaction isn't fast enough for us to see it yet. But I doubt that. Based on the timescales, based on how quickly we went from, when I went from the titration of 40 to 50, so I added 10, that was over a course of 2 minutes, where I saw nothing to seeing something. It could be that in 0 through 40, potentially our ECP, it's our nerve agent, it's our phosphorus agent. Remember how I said earlier, phosphorus really loves to make oxygen, or loves to make phosphorus oxygen bonds. They're really strong. So perhaps the first few aliquots of my titrant are being consumed by the water present. Maybe this is actually a way to get the water away, possibly. I also don't think that that's the case. I would have to do some mass spectrometry to see if that's why, possibly, or some NMR. But we don't think so. And then finally, these peaks show up, but the peak doesn't grow. Notice that. We end up with the peak, this spike leveling off right about here, and then this peak doesn't grow any further. So not a sensor. So that is the death. So from here I go to my advisor, I show her, oh, hey look, here's my results. And she kind of looks at them, frowns.
Oh no.
Oh.
Ouch.
And about 6 months ago, our funding for this project dried up. So what happens when a granting organization gives money to you, they give you X number of dollars over X number of years. So for this one, I think we had $400,000 over 4 years to produce results. 4 years came up, no results. So pretty much the funding's gone. And another thing that I should mention, in the past 3 or 4 years, really, there have been, I don't have the exact number, but I'd estimate about 800 publications out there on detecting nerve gases, because, as I said earlier, there's about $10 to $20 million pumped into the economy to academic labs saying, solve this. Other people came up with their solutions. So between our results not working in time, and the fact that essentially the problem's already been solved, other labs got to it, there was little point in going forward. So what does that mean for me? Because I've been there for a year. Well, it's okay. So the new kind of thought behind doctoral students in chemistry getting their PhD is that you tend to work on about 3 projects now. So the projects will hopefully be interrelated, but they don't have to be the same thing. They don't have to be driving at the same point. They don't have to be answering the same question. So more than likely, this result will never get published to the general scientific community, other than you guys who got to be here for the funeral. But nobody else is really going to learn about it, that's troublesome for a grad student, because that's really the way of getting the next step in your career is by other scientists learning about your work. But when all is said and done, I have to write this thing called a dissertation. It's going to be no fun. But typically you have several chapters in your dissertation. Each project will lend 1 or 2 chapters to it. This work, even though it's all we learned what doesn't work, still actually gets to be part of that. And now I get to move on to a different project. And actually you might think I'd be sad to have like a year of my life poured into research that doesn't work. But there's hope. There's hope when there's a new project. It's kind of the light on the horizon. I get to do something new, something maybe fun, something unexplored yet. And the next thing is, as always when you're trying to do science, you're starting to answer a question that nobody's really answered yet. So I was trying to answer a question that everybody else answered. My next question, almost nobody's working on. So there won't be very many people to beat us to the punch. And then at this point, I'm always obligated to put in like a further work section. So further work is really none. We're scrapping the project. But there's a whole lot of things that could be done. You could do gas phase experiments if we sent this off to a lab that has the ability to test nerve gases without killing everybody in the room. There's also, sensors must be specific. You don't want to end up accidentally sensing something else in the environment or in the solution that you're working with. So there's a whole wide range of specificity tests that need to be done with those candidate sensors as well. But as you saw, none of them really passed all the tests to become a sensor, so dead in the water. So I will show you, many people answered this question, right? I'm going to show you probably one of my favorite answers to this. So this group, they're a Spanish group led by Ana Castero, I believe University of Valencia, if I remember. They actually, what they did is they developed 16 different dye molecules. You can see several different families. These groups have a metal and a porphyrin ring or a porphyrin analog. Some of them have, you can see here we have diazo compounds, and some of them have just basic organic dyes with like a shriveled group. So what they did, they said, all right, we have 10 or 12 different nerve gases that NATO has recognized they want us to be able to sense that are all similar. Well, how do you make sure you're detecting something? How do you make sure you detect just one particular thing out of a wide range of similar groups? So what they did, they actually had these 16 dyes. They developed a 4x4 grid with them. And now each different nerve agent that's being used here has a different fingerprint, has a different signature based on the slight variations in how it interacts with those 16 different dyes. This got a lot of press. This one was very popular because it is a very elegant solution to this. I mean, now you don't have to bring a mass spec out into the field. All you need is an ocean optics sensor and your grid panel, and a little adapter so you can fit your ocean optics right over that grid. Expose it to the gas, and then use those results.
Is their test quantitative?
No, that's qualitative. They do have a threshold. I believe it's 0.9 ppb for atmospheric concentration, if I remember their threshold right. And it does vary slightly across these. You can also see they also tested hydrochloric acid gas on here, which is not a nerve agent, but is a possible nasty weapon. I think I remember one time ago a lab where a little bit of this got up in the air. That was no fun. You can see here different fingerprint. And so that was really cool. And we basically said, we looked at our results, what we were getting, and what we hoped to do, and said, can we beat this? And we just decided, let's move on. So that is ultimately what happened. And I'd like to thank Dr. Arthur Schaffers as my advisor, who got the money for this, got the grant. Dr. Lars Kohler started a lot. So I said 4 years we're on this grant. Really, you saw just a snippet of research. There's a lot more research done, and then, along with a lot of synthetic chemistry developed for us to make our compounds. That was mostly done by Lars Kohler. Kim Huen and Marcus Moses were two undergrads that worked on synthesizing some of these sensors. Jared Wabeck helped with collecting spectroscopic data, along with funding departments. So thank you for listening. Sorry to take you through a funeral with a really boring eulogy, but that's that. So I'd be happy to take some questions. Also, if you have any questions about grad school in general, what it's like at Western specifically, what it's like to have a family in grad school, you can ask those. I'll also be around most of the day here, either over in the DC or in the library. So if you want to find me later, let me know. You can apply for the RU. It's a good idea. And let me know if you apply to Western. So thank you.